Now to a phenomenological discussion of the process of diffusion. So if I, for example, put a little drop of coloured dye in a beaker of water and ask how that spreads out under the influence of thermal fluctuations into the most probable state entropically with the dye uniformly spread out over the beaker. Another example would be if I applied heat locally to some point in a medium through which it could diffuse. So turning to the picture on this slide, if we consider a little elemental box inside a material through which particles or heat are diffusing, and make the box sides delta x, and then have a flux entering the box, J of x, and a flux leaving the box, J of x plus dx. Then if J is the number of particles per unit area per unit time, the concentration in the box, or the change in concentration, must just be equal to the area times the flux out times a unit of time minus the area times the flux in times a unit of time. And then that's the number of particles that accumulate in the box, so we then divide by the volume of the box. Taking the calculus limit, letting delta x and delta t go to 0, we arrive at the following partial differential equation for the concentration inside the box as a function of distance and time. And it says that change in concentration with time is directly proportional to the change in flux across the box with space. So we can rewrite this equation by expressing the flux as a change in concentration times the velocity of the particles. In other words, the net flux must be equal to the concentration of particles at a point times the velocity with which they leave that point, and this leads to the expression on the bottom of the slide that J is minus dc dx, where we have now multiplied top and bottom by dx, or equivalently delta x. So from this then we can derive another equation that's shown on this slide here, using the following definition, and we'll see why this is a good definition in a second, and the result we just obtained, which is that we had J proportional to dc dx with this coefficient in front of it, so that now becomes minus d dc by dx. This is called Fick's law. It says that the net flux is related to a constant, the diffusion constant, times the concentration gradient. If we substitute this into the result we had on the previous slide, we then obtain the diffusion equation. So we've substituted for J now in that equation in terms of d by dc dx, and we had the first derivative of dc dx in the equation on the previous slide. So now we get two minus signs cancel out. So the diffusion equation says the change of concentration with time and position per unit time is equal to the diffusion constant times the second derivative of the concentration. The solution to this equation in one dimension, which I will just quote without proof, is this. So the plot shows you plots of this solution starting out at some small time. You can see it has the shape of a Gaussian in space, but also like 1 over the exponential of time in time. And what you see is that the a distribution that's originally like this flattens out with time and broadens, as one would expect, as entropy is maximized. Now, if we take a look at the half-width of this distribution, in other words, we ask how far does the halfway point of this distribution move in time, we obtain the result that this half-width is the square root of 2 dt, approximately. I'm ignoring the term in front of the Gaussian. Now, you see once again in this phenomenological description that we have a motion under random thermal driving forces in which the position of something changes like the square root of time. So this square root of m is clearly a very common result in the theory of fluctuations. And let me justify it here with a very general argument about random walks. So a random walk or a drunkard's walk can be thought of, let's take a drunkard who takes a constant number of steps per unit time, but they are in random directions. So here's the lamppost where the drunkard starts out, and then we just add together all these vectors, but we do it randomly. And our question is, how far has the drunkard gone after some time? Well, of course, we know that the average distance that he gets is 0. He always ends up at the lamppost again. But we can ask, what is the range of the fluctuations around the lamppost? And for this, we need this quantity r squared. So if we then just form, if r is this sum of random vectors, if we form this square now, where this is a pair of random vectors, and I'm setting the problem up this way in order to explicitly show what happens to various terms in this. For all the terms for which I equals j, we get a positive number, and that's equal to the magnitude, it's just r squared, which is the magnitude of the step. And let's say his step size is a, and if there are n such steps, he takes a total of n steps. We then have this result. Plus all the terms for which I is not equal to j of this product. But in general, this goes to 0 because these vectors are not aligned with one another because they are random. So we see that the mean square distance that is moved is proportional to n, or the root mean square distance is proportional to the square root of n. We end by returning to our problem of diffusion and taking a look at the two results we obtained. One was from the diffusion equation that we just considered, where we saw that the dye that we added diffused out according to x is the square root of 2 dt. Recall, though, for the Langevin equation, we obtained the following result, that x squared was kt over 3 pi eta a times t, and comparing these two, you see then that the diffusion constant is given by kt over 6 pi eta a. This is an example of a general relationship first derived by Einstein and Smoluchevsky, called the Einstein-Smoluchevsky relationship. If we take 1 over the friction coefficient to be a mobility, which we call mu, the general statement of the Einstein-Smoluchevsky relationship is that the diffusion constant is kt times a mobility. It's a very general result, surprising result, because it relates the motion of a driven particle, the mobility, to the motion of a particle moving under random thermal fluctuations.